Okay, so let's get started. So I'm going to present to you what AirScript is. It's a unified language to express Stark constraints. I'm going to dive into what that means. Okay, sorry. I'm going to dive into what that title means. So let's get into it. First off, a little bit about us. We are Defined Innovation. We are a subsidiary of Massa Labs, where we do advanced R&D on mathematics and software projects. Let's start by talking about what ZK Starks are from a really high-level perspective. So you basically start with a program execution. You trace all the values in your execution. You then pass it through something a bit magical that we call ZK Starks. It generates for you a proof. Now, what does that give us? With Starks, you basically get proofs that are small with respect to your execution time and the size of your trace. You get fast verification compared to proof generation and even compared to re-execution, which is how ZK rollups can scale. And you also get relatively fast generation, at least compared with other snarks. Let's get into it. There are a few protocols today that are using snarks. You probably all know Starknet. There is also Polygon Miden, which is where I work right now. And maybe you've heard of ReZero. Those are protocols that are using ZK Starks to perform various things. So how did we do things in ZK Starks before AirScript existed? We had to handcraft everything. So this is an extremely manual process, which can be very error-prone. Auditing them is extremely hard because you have to audit it knowing exactly which framework you're using. That means your auditors need to know the specific framework you're using as well, which can be fairly tough to find someone who's able to do it. You don't have any way to migrate from your current prover to a new one. So that's something that that's something that AirScript will enable. It also cannot be easily optimized because you write everything by hand. If you need to optimize things, you need to optimize them by hand. So that's very complex, very tedious, and again, really hard to audit. So let's get into what AirScript really is. AirScript is a language that lets you express Stark constraints in an expressive, modular, and auditable way. It can target several backends. When I'm talking about backends in this context, I mean a compiler backend. So that means that's the code it outputs. Currently, we support Winterfell, Miden assembly, but we do plan to add more in the future. AirScript has a few goals, like I've mentioned, but let's go a bit deeper into it and what that means. We aim for AirScript to be human readable, which should facilitate auditing. We do plan to add formal verification as part of the pipeline so that you can be sure that the thing translated corresponds to the right thing and that all your constraints are really satisfied within your system. It is an expressive language, so you can compose components quite easily together with fairly minimal restrictions. It is a modular language, so once you created a module to do something specific, you can reuse it anywhere. You only need to audit it once, you can reuse it, several times. It allows interoperability through the use of several backends, like I've already mentioned. And finally, it automates optimizations. I'll go into a bit more details into those, so here is the list if you're interested, but we'll get into them. So what does AirScript allow you to do? I apologize first, I didn't expect the code to be so hard to read. I'll be posting the slide afterwards, so feel free to check out my Twitter while I'll post them. So AirScript supports the notion of functions, kind of like any other language. You specify input types, output types, and then you can call them. That lets you reuse existing code without having to handcraft everything. We support loops in the form of list comprehensions for those of you who are familiar with Python and how those are used there. And we finally support modules, which is how you can have a single piece of code that does something very specific. You audit a specific piece, now you can reuse it within the system and have more guarantees that it's correct. Now let's dive into the optimization like I promised. First off, let's take a look at the full compiler pipeline, at least from a high level. You start with your AirScript source code. We first do the normal thing that we do in compilers. We parse it into an abstract syntax tree, perform semantic analysis, constant propagation. So far, those are fairly standard. We then translate them to an intermediate representation that's more suitable to make optimization. It's less specialized to the language itself, so it makes things a bit easier to use. As part of those optimization, we currently support function inlining and loop unrolling. Those are total, so every function that gets called anywhere always gets inline. Every loop that's present anywhere in your code always gets unrolled. So you have the guarantee that once all of this is done, you have a static graph at the end, because what we're trying to compile to are circuits, and those need to be fixed in size. Then we do plan to add more optimization, such as constant common sub-expression elimination, dead code elimination. Those are not fully implemented yet, only partially functional, but we are still working on it, so that should come fairly soon, which should help make your chiplets a bit more efficient. It then generates an algebraic graph, which we'll dive in a bit deeper. The algebraic graph is then passed to the CodeGen module, which will be used to target several backends. Like I said, those are compiler backends. So we can target a Winterfell prover, which means that what the constraints you express in AggScript can be verified through Winterfell. We also do it for Miden assembly, and I'll dive a bit deeper into why that's useful. But first, let's talk about what chiplets are. Chiplets are basically single units of code that you are able to reuse. That's how we make things modular. Right now, here is an example of what a VM in AirScript, a ZK VM, would look like in AirScript. So you'd have an ALU, which lets you do arithmetic and logical operations. You could have, for example, a hash chiplet, something that calculates a hash that's been audited that you want to reuse. But if you want to go really deep, you can even have a full stack verifier as part of your chiplets. These components need to communicate with each other, and that's done through that bottom part in blue, which we call a bus, which is what we're going to talk about now. So once you have several chiplets, you need to interconnect them with each other. Right now, here you can see a small chiplet that does an addition between values A and B and outputs a value C. So as you can see, it reads the two values from the bus and it outputs it to the bus, which is then used by another function, here a hash chiplet, which again takes in the value from the bus and outputs it back to the bus. So that's how you interconnect all your chiplets without having to replicate all your chiplets as the output of every other chiplet. Okay, so I expected the code to be a bit more readable. I apologize about that. So now I'm going to describe it, at least from a high level. We have two kinds of buses. For this talk, I'm only going to talk about the simpler one. We call them the unit buses. Within AirScript, we enforce what we call boundary constraints, which basically tell you what should be the state at the beginning and at the end of your execution. Right now here, we enforce that the bus starts empty and it ends empty throughout the execution. We then enforce what we call integrity constraints, which basically tell you how different lines in your trace are linked with each other. What are the relationships with each of the values? Or do we enforce that they are correct, that the computation was done correctly? There are two operations within a bus. You can add a value and remove it from the bus. Those two operations are constrained with signals, which I call here S1 and S2. As you can see, when S1 is available, the value is within the bus. When S2 is available, the value is within the bus. They are both independent with each other. What you need is that the value is present when you need it. That's what you're going to try to prove. This was meant as an example of AggScript, so again, I apologize for the readability. This is a Fibonacci example. So we declare two trace columns, which are the values that we're going to track throughout our execution. We'll name them A and B. This is a fairly simple one, only Fibonacci. So we enforce within our boundary constraint that our value starts at 1, both of them. We say that we have no public input because program is fairly simple, but you could actually have some programmability via those public inputs. We then enforce that the next value of A is always equal to the previous value of A and B, that's at least, and that the previous value, that the next value of B is equal to the previous value of A. And that's about it. So, to give you a rough idea of where Miden describes itself, first off, I don't expect you to be able to read this diagram. I just couldn't find a way to fit it in a slide. So just get a rough overview of what it looks like. Now we're gonna zoom on the last bit. AirScript is basically the cornerstone of Miden VM. It's what enables recursive proving. And so, yeah. Like I said, it's what enables recursive proving. You do it by expressing the Miden VM constraints within itself. You compile it to itself, now you can verify itself. There are several future avenues for AggScript. For example, we could talk about interoperability. You could have an EVM written in AggScript such that you would be able to verify the execution of Solidity smart contracts. You could have a RISC-V VM in order to verify the execution of any language that compares to RISC-V, which are still quite a lot of them. You could also have a Caro VM in order to verify the execution of a smart contract on Starknet. But that's not the only thing that I'm interested about. We are also interested about making hardware acceleration possible with the use of VHDL provers. So that's about it for this talk. It was fairly high level. We are currently looking for partners, financing, collaboration opportunities. So if you're interested, please reach out to us. I've let our emails on the slide. You can also find on Twitter, and there is my Telegram out.